Today, we all know that the world is facing energy crisis. Scientists all over the world are trying to make energy-efficient devices, either at the generating end or at the consumption end.
Our project is funded by the National Science Foundation, specifically under the Center for Energy Efficient Electronic Science, E3S.
The design we're currently working with is called a SQUITCH. It's not a switch, it's a squeezable switch.
We're trying to create more efficient devices, and it really comes down to the small components within our electronics that we need to make efficient.
The problem with conventional transistors, silicon-based transistors, is basically that in order to get them to work faster, we need to increase the power consumption. And we don't want to go down that route because, we're aiming for more and more efficient electronics.
To make our devices in the simplest form, we start with depositing a thin film of a metallic contact, let's say gold. And then the molecules, our organic molecules, are self-assembled on top of this metallic contact. And on top of the molecular layer, we put a second layer of metallic electrode.
Now, these molecules have a property that they can be squeezed. So when the electrodes move together, the molecules squeeze, storing this energy. And then when you need to turn off the switch, these molecules can release the energy and get the switch back to its original place.
So traditional MEMS switches have contact, metal-metal contact. So a cantilever will move, make contact with the metal, and then when the voltage is released, the cantilever will also be released. But one of the traditional problems is what we call stiction, and the metals will bond together, essentially, and it takes a high voltage to break that bond. What we're trying to do is to not ever have that metal-metal contact by having the organic molecule in the center and tunneling through that organic molecule.
So what I love of this project is its interdisciplinary nature, right? We have physicists, electrical engineers, chemists, material scientists, all working together. And everyone thinks differently, but then everyone has this common goal, and which really makes it exciting to work with.
If we can make sub-1 volt devices and get them to reliably work in systems and technologies, we're definitely going to see a huge change in the size as well as speed of our electronic devices.
It is very possible that, down the line, this technology can evolve, just like how silicon transistors evolved over a period of 50, 60 years. This technology can perhaps evolve to a stage where it can be so commonplace that you can find it in pretty much every consumer electronic device out there.
So we are a step ahead of the conventional switches. Conventional switches still work at nanoscale, but they are still not at the molecular level. What we are trying to do is work at one molecule level, a level at which everything in the world is made up of. And that's what makes it challenging. But if it does work, then I feel that this will lay a foundation for the next generation devices.